Hello, am I audible?
Hello, good evening, sir. Yes, sir, you are audible.
Yes, sir, you're audible.
Thank you. Okay, so in today's session, we'll be revising the concept for quiz 2. Okay, so the syllabus for quiz 2 is basically from week 5 to week 8. Okay, so this is the first session, and we'll try to cover week 5, week 6. In the next session, we'll cover week 7 and week 8. I hope I'm audible properly, right?
Yes, sir.
Yes, sir.
Okay, fine. So let me share my screen. Yeah. Yeah, so you can see the syllabus for quiz 2. So it's from week 5 to week 8. But if you see, almost 70% of the paper will be based on what? Week 5 and week 6. Okay. Very important topic, normalization concept, week 6. And this completely depends on week 5. So we have to prepare week 5 and week 6 because it consists of 70% of this weightage for the quiz 2. Okay. And week 7, week 8 is also important, right? So in today's session, we'll try to cover week 5, week 6 entirely. Okay. So if you look at the week 5 topic, right? Week 5, we have started with what? The concept of functional dependency here. Okay. Functional dependency. Then based on functional dependency, we have discussed how to find out the closure of an attribute. Closure of an attribute, right? Then we have discussed how to find out the keys. Okay. Keys here, then candidate key, number of super keys. So how to find out candidate key, super keys, and number of super keys, right? Then we should be able to find out what decomposition here, right? So we have discussed about the lossless and lossy decomposition here, right? So lossy and lossless. Then in week 5 again we have a concept of a dependency preserving. Then see preserving, right? So here's a few important topic that we have discussed in week 5. Also, if you look at the properties of functional dependency we have discussed, right? So that is about the week 5. In week 6 is basically about normalization here, right? So we have discussed various normal forms, right? So we have to discuss various normal forms, 1NF, 2NF, then we have 3NF, then we have BCNF, right? Then we have 4NF that deals with what? MVD, multi-value dependency. So we have to focus on this, but for to solve the question from week 6, we should know the concept of week 5 first. Okay. So first, let's start with the functional dependency here. Can anyone tell me what is functional dependency? What do you understand when I say A determine B? What do you mean by A determine B? Yes, anyone?
The
B
the
is
attribute
functional depend on A.
B is function dependent on A, or I can say A uniquely determines B, right? A
Yeah.
uniquely determines B here. So if I have a relation and here we have three attribute A, B, C. If A1, then we have B1, then we have C1, then A2, we have B2, then we have C2. A3, we have B1, then we have C3. Then if we have one more A1, right? So if I say A determines B holds to here, then A1 should determine B1 only. It's not like that A1 should determine B2. If in a table, if A1 determines B1, also A1 determines B2, it means what? FD is not holding there, right? So A uniquely determines B here. If A1 is determining B1, then A1 should determine B1 only. Okay, this is about a functional dependency concept. A uniquely determines P here. Okay, this is about the functional dependency. I hope any doubt here how FD works here? Simple. A uniquely determines B. So left hand side uniquely determines right hand side. It is possible that A1 also determine B1 and A3 also determine B1. It is fine. On the right hand side, it can be duplicate as well in the table you can see. But left hand side must be uniquely determines right hand side. And this is what FD is. Now let's say, for example, we have a relation having A, B, C, and D here. We have four attributes, and the FDs are basically like this. Let's say A determine B, Then we have B determines C. Let's say, for example, we also have A determine D as well. Okay. This is FD set is given to us. Now, if I need to find out the closure of A here, so how to find out the closure of A? Yes, anyone?
First, look up the right hand side of the FDs.
All
And
four, sir. A, B, C, D.
Yeah, see, first, trivially A will determine A itself, yes. But from A, what I can get? From A, I can get B, so I'm going to add B. Now I have to check from A or from B what I can determine. From A, I can
C and
also
D.
get D here. I can D here as well. But from B, I can get C as well. So I can add C also here. Okay, so this is what my closure of an attribute is. Okay, so we'll be discussing more about the closure because in every question we need to find out the closure here. Okay, so this is how we can find out the closure of any attribute. Okay, let's say for example, if I want to find out the closure of A as C here, right? So first AC will include AC itself, but from A or from C or from AC, what we can determine from the FDs that we can add the attributes here. For example, B and D like that. Okay, so anyone any doubt how to find out the closure of an attribute?
No, sir.
Okay. Now, what about the candidate key here? How to find out candidate key? What is candidate key first? Yes, anyone?
uniquely identifies that
All the
each
attributes.
row.
Yeah.
Uniquely
It uniquely identifies the row of a particular table, we can say. Okay. So we can say uniquely identifies a row of a table, or we can say tuple, right? But this is the definition of key here. Okay, in general we can say this is also applicable to super key as well. It also uniquely identifies a row in a table. But what are the difference between candidate key and super key? Yes, anyone?
super
Unique
key
and
is a
multiple.
subset of super key is a superset of candidate key.
Super key is a
Super
superset of
Candidate key is a minimal set of attributes that identify.
yeah. So we can say candidate key is basically a minimal a set of a super key, we can say, and every candidate key is basically a super key. So every key is basically super key, we can say, but candidate key is basically a minimal of this particular super key. Okay, so how to find out candidate key here? If I say this relation and this FD, how to find out the candidate key?
Find out the attribute which is not in the right hand side of the functional dependencies and find out the closure of that attribute. If it contains all the attribute of the relation, then it is a candidate key.
Correct. So we can follow one trick here. So first we need to find out which attribute are not present on the right hand side of any functional dependency. So you can see B is present, you can see C is present, you can see D is present. It means what? A is not present on the right hand side of any functional dependency. So first we have to check whether A is candidate key or not. The attribute or state of attribute which are not present on the right hand side of any functional dependency, that must be a part of candidate key. We are not saying that it is a candidate key, that must be a part of candidate key. But first we have to check whether that is a candidate key or not. So for checking how we can do that, simply take the closure of those attribute or set of attribute. You can see if I take the closure of A, I'm already getting all the attributes here. So if in the closure of any attribute or set of attribute, if you are getting all the attributes of that particular relation R, it means what? That is basically a key here. So you can see A is basically my candidate key here. Okay.
Sir, in short, candidate key should determine all the attributes, right?
Yes. Any key, candidate key or super key should determine all the attributes here. So if I take the closure of any key, that should give me all the attributes in the relation R. Okay. So here you can see A is basically my candidate key here. Now, if you look at AB, AC, AD, or ABD, this all will be my super key. So I can say that the combination of the combination of candidate key with any other attribute, that is basically my super key here. Because here you can see if A can determine all the attributes, it means AB can definitely determine all the attributes. If A can determine all the attributes, then AC also can determine, right? So these all are my super keys here. So combination of candidate key with any other attribute, that is basically a super key, and this A is also super key. Okay, so every candidate key is basically super key as well. So that's why we said if AD is my super key, then we are finding out the minimal of this particular super key is my candidate key. Minimal set means what? Either A can be candidate key or D can be candidate key here. So minimal of this D can be a candidate key here. But if you look at A is a candidate key, so that's why AD is basically my super key. Okay. So if I say the combination of candidate key with any other attribute is basically my super key and candidate key itself a super key, then how many candidate keys are there? How many total candidate keys are there? Sorry, super keys are possible for this relation.
8.
How many total? Okay, how to find out those?
2 raised to 3. The remaining total 4 attribute are there. Then
2 raised to n power
2
2
raised
raised
to
to n
3.
minus 1.
Yeah. So to find out the number of super keys,
n
to
minus
find out number of super keys, we have 2 to the power n minus m here. Now n is basically what? Total number of attributes in relation. Number of attribute in relation R. Okay. M is basically what? Number of
candidate
attribute
keys.
in number of attribute in candidate key. Okay. So here if you observe, here we have one candidate key, right? That is basically A. So attribute is only one. Here we have total 4 attributes. So n is basically 4, m is basically 1. So 4 minus 1, that is basically 8 here, right? So this is only for one candidate key A. But what if I have this relation A, B, C, D, and my candidate key is A and C, both? In that case, how to find out number of super keys? So this is basically case 1. So here we have a case 1. Case 1 is basically what? Only one candidate key is there. Only one candidate key is there. So we already discussed about this particular thing. That's it. Now case 2 is basically what? We have 2 candidate keys. 2 candidate keys and the intersection is null here. So when I say intersection is null, so A, B and B, C. If I consider this to as candidate key, but here B is common. So this is a different case here. But right now we are discussing about this one. If A and C both are the keys, so here we deals with A, but here we are dealing with A and C. Now tell me, if we have 2 candidate key A and C, how to find out number of super keys in this case? Yes, anyone?
That is 2 raised to 2.
Define the
2.
closure like first for sorry 2 4
2
minus
to the
4.
power 4 minus 2 is
Yes.
equal to 2 to the power 2.
So here, if I write this formula, it is for a particular candidate key. So from this candidate key, we can get this much number of super keys. Okay. So here we have 2 candidate keys here. So from A, how many candidate key I can, how many super keys I can get?
2.
To the power
2.
4 minus 1. That is basically 8. From C, how many I can get? Same thing, to the power 4 minus 1. That is basically 8.
Yes.
Because if you
We have to
see
add
from
a-
so from A also I can get A, AB, ABC, ABCD, ACD, all those things. In case of C also I can get all those possible things. But if you observe here 8 I have written. In the case of A, you can see ACD will be a key. In the case of C also ACD will be a key. So there's a repetition in
Yes,
this
sir.
particular thing. So what we have
Minus
to do? We have,
intersection of
We have
both.
to intersection
of both.
yes. So we have to subtract this one. So you must have seen this number of A, then that is
Union.
basically union B is equals to n of A plus n of B minus A intersection. This is A intersection B union of B. So A and B are 2 different candidate keys here. A and B are 2 different candidate keys here, remember. Now let's say we have A as A and we have B as C. So we already calculate this one, that is basically 8 plus 8 minus, we have to subtract the common here. How? A union B means what? A union C means AC here, right? So AC we have 2 attributes, and if I apply this particular formula, so to the power 4 minus 2, that is basically what? 60 minus 4, right? So 12 will be my answer here. So if I have A and C, the answer will be 12 number of super keys. For 8, there will be 8 super
Sir,
keys.
can you, if you don't mind, sir, can you solve for AC in formula?
AC, okay. So if there is only one candidate key, and that is basically AC, in that case, the value of M will be 2. So that is basically 2 to the power 4 minus 2. That is basically what? 4 here. Okay. If only AC is my candidate key. If A is candidate key, the super keys will be this one. If AC is a candidate key, the number of super keys will be what? According to the formula, this one. But if A is different candidate key and C is also different candidate key, in that case, we have to go with this particular thing. Is this
Yes, sir.
clear? Any question? Anyone?
If all our candidates
So that
were separately, like A, B, C, and D, if they're all are candidate keys, then 2 power n minus 1 is the formula. 2 power n
Yes.
minus of 1.
Minus 1. Yeah. If all the keys are basically if all the attributes are basically a candidate key, in that case, to the power n minus 1 will be the to the power n minus 1. This is the formula for that. Okay. If all
Sir, for
A,
what?
this is formula when all the attributes are individual candidate key here. It means A is also candidate key, B is also candidate key, C is also candidate key, D is also candidate key. So individually all are candidate key. In that case, if all the attributes are candidate key, so to the power n minus 1 will be my number of super keys.
Yes, sir.
Okay.
So, but if AC is a combined candidate key, then
Yeah. If AC is combined candidate key, so you can see here there is only one candidate key. So the value of m will be 2. So to the power 4 minus 2 here. Okay, that is basically 4.
yes,
So here m deals with what number of attributes in candidate key. If AC is the
this
key,
union and intersection formula is for the different candidate keys, right?
yeah. If we have two candidate key, in that case only. Okay. So if we have two candidate key like this, one is AC and second is BC. So these two are different candidate keys. Now in that case, tell me how many super keys are possible. So first we need to find out using AC, then find out using BC.
So
Let's
3.
here. So for AC, how many candidate key will be there? To the power 4 minus 2, that is basically 4. For BC, again same thing, 4 minus 2, that is basically 4. But we need to subtract the common one as well. So here A union B is basically what? ABC, right? So AC union BC is basically what? ABC, right? Now by using ABC, how many candidate key we can get? By using ABC, to the power 4 minus 3, that is basically 2 here. So 4 plus 4, 8 minus 2, that is basically 6 will be my candidate key here. Sorry, super keys here. So remember this particular formula here, okay? So first find out the number of super keys using one candidate key, find out number of super keys using another candidate key, minus, then you have to take the union of that, like that we have what we have taken, and number of super keys using that union, and then we have to subtract from these two. Okay, summation of these two. This is basically third case we can say. Here we have two candidate key, but here something is common between them. Anyone, any doubt here? How to find out number of super keys? Any question?
In the case of all the attribute are candidate keys, in which case how many super keys are there?
To the power n minus 1. That is basically in the case of all attributes are basically my candidate key. This is the formula. If all attributes are individually a candidate key, means A also candidate key, B is also candidate key, C and D as well.
That is the same in the case of one candidate key.
No, individually here we have 4 candidate keys. All the attributes are candidate key. A is also candidate key, B is also candidate key, C is also candidate key, like that. In the case of A, we are writing this n minus m, so that is basically n minus 1. But here to the power n minus 1, like that. It's not n minus 1. To the power n, then minus 1, like that.
Okay. Minus in the, not in the exponents.
No, yeah. Okay, this is how we can find out number of super keys here. Okay.
So I have a question.
Yes.
All the attributes are candidate key. It means that every attribute is not dependent on other keys, or like what it means. I can't get
Yeah.
that point.
So if I say every attribute is candidate key, so each attribute can determine another attribute as well. Okay, like that.
Okay. For example, in this
Each
case,
attribute will be determining the whole R, right? That means
Yes.
every attribute is a candidate key in that
Yeah.
case.
So A is also determining A, B, C, D. B is also determining A, B, C, D, like that.
Okay, okay.
Yeah. Okay.
Every attribute is a contributor, like.
Yes, we can say. And let's say, for example, in any relation, we just have this relation A, B, C, right? We just have this relation R, A, B, C, and there is no FD applicable to this. No functional dependence is given. If FDs are given, then we can find out the candidate key by using this rule, okay? What we have discussed earlier. But what if there is no FD applicable to relation R? In that case, what will be my key? Yes, anyone?
ABC.
Yes.
So we will check by closure.
No, if there is no FDs, it means what? Combination of all attribute will be my key here, A, B, C, right?
Yes.
So here A1, B1, C1. So if I say combine the candidate key, it means what? I cannot repeat the same row again here in the table, right? So entire combination is a candidate key in that case, if there is no FDs applicable. Okay. So it is possible A1, B1, C2 can be there because it's a different thing, right? Like that. So this is about how to find out the candidate key number of super keys. But here we have just discussed when the attributes are present on the right hand side of functional dependency. What if attributes are okay? What if all the attributes are present? Let's say for example A, B, C, D, and here we have F, D as well. A determine B, B determine C, C determine D, and D determine A. In that case, what to do? All attributes are on the right hand side of FD. And how to find out the candidate key in that case?
You need to
So
check with also.
A is also candidate key, B is also candidate key, C is also
Yeah.
candidate key, and
Every
D is
attribute
also.
is candidate key.
No,
Because if we
here,
check closure for
uh,
any one of them, it will give the whole series.
yes. So here it's a simple one. So we can easily find out all attributes are candidate key. But if I'm saying, let's say for example, AB, then we have CDA like that. Okay. Don't have this FD. So B and CDA is on the right hand side of FD. So that rule will be not applicable here because all attributes on the right hand side. In that case, what you need to do? You have to take the closure of each and every attribute and see whether it's key or not. Find out the closure of each and every attribute and see it's a key or not, like that. Okay. So there are a few questions. We will discuss that. Okay. In those cases, how to proceed.
Sir, and all the attributes are also super key.
Sorry, all attributes.
All attributes are, if all attributes are candidate key, then it also all attributes are super key.
Yes, yes. So every candidate key is basically super key, or we can say every key is super key. That's it. Every key is super key here.
So,
Okay.
but every super key is not candidate key, right? May or may not be candidate key.
So minimal set of super key is basically candidate key. Minimal of super key is basically my candidate key here. Okay. If I say A, B, C is my super key, so it can be possible that A is a candidate key, or B is candidate key, or C is candidate key, or AB can be candidate key, or BC can be candidate key, or AC can be candidate key, like that. Okay. So minimal of that super key will be my candidate key, like that. Okay.
Sir, in this condition, when everything is on right side,
Hmm.
we need to take the closure of only A and B.
No, no. If everything on the right hand side is present, so
In this
check the
condition,
attribute. Yeah. So check the closure of all the attributes here, A, B, C, D. Okay.
which are
So,
on in which are in FD's left side of the FD's or all?
no, if so, first we have to check the attribute which are not present on the right hand side of any FD. But if you see here, all attributes are present on the right hand side. So in that case, we have to check for individual attribute here, whether A is key, or B is key, or C is key, or D is key. If I found A and D are the key, but BC is not the key here, then I have to check for the combination of BC closure as well. So BC is also possible candidate key. So you have to find out all the possible combination which can be a possible candidate key in that case. Okay. So you have to work out that.
In this condition, how to take closure of C?
So for this thing, if I just take the closure of C will be C only. We don't have anything here, right? We cannot determine anything.
Yeah, so that is only I wanted to ask. We need to check the
closure of left hand side of the FDs or all the elements, sir?
All the attributes.
Sir, could you solve this problem, sir? This question which you have written, like, could you
Uh,
find the candidate keys? Like, it would be more
for
clear.
for this one, A, B,
Yes,
and
sir.
B,
Yes,
D,
sir.
C, D. Yeah. So if you look at here, A, B, and B, C, D, A, right? So first, all attributes are present on the right hand side. So what I need to do, I have to check the individual attribute here. Okay. So first I will check whether A is candidate key or not. How I can check? Simply take the closure of A based on the FD. So from A I can get B. From B I can get C, D, A. So that's it. All attributes are present. So A is my candidate key. Now we have to check for B as well because multiple candidate keys are possible. Now to check for B. From B I can get C, D, A. Right? So that's it. All attributes are present. So B is also candidate key. Now I have to check for C as well, whether C is candidate key or not. So from C I can get only C here. Then I have to check for D as well, whether from D I can get determine all the attributes or not. But no, D is also present. Now I have to check the combination of C and D as well. The from CD can I get A B C D as well? No. So here CD is like that. So I have checked for all the possible combinations here. Then I can say only A B is a candidate key.
They are
Okay.
separately candidate keys, right, sir? A is a
Yes.
candidate key and B is a candidate key, right?
Yes. A is separate
What
candidate key. B is separate candidate key here.
if we combine A, B, what could you comment on that? That is also candidate key or that would be a super key? What?
That is basically super key. A B is basically super key.
If there is no intersection between like if B is separately determining some other attribute which is not there in A, then if we combine A, B, it would become a candidate key, right?
No, if A is a candidate key and B is not a candidate key, if you combine A, B, that is basically super key only.
No, sir. What I'm saying is, if A is determining some like for example, A, B, C, D are the determined by A plus. If B
Okay.
plus is determining some other candidates, for example, E and F is also there, which is not determined by A.
Okay.
When we take A B closure, then we will get all the attributes, right?
Yeah.
Then can we say that B plus is a candidate key?
Yes. In that case, A B will be a candidate key. Okay.
Okay.
So if I have A B C D E F as my relation, and if I take the closure of A, I am only getting A B C D, right? So it means what? I am not getting all the attributes here. It means A is not candidate key. But if I take the closure of B here, I am getting what?
B E F.
B, D, E, F, let's say, for example,
Yes.
right? That is also fine. But here A is missing here. It means A is not candidate key. So you have to take the combination of B with the attribute which is not present inside the closure. So A is not present. It means what? I can take a combination of A with B. So together A, B can be candidate key here, like that. Okay.
Yes, sir.
Yeah.
Sir, if there is a two candidate key, we can combine this as a candidate key. It is a super key, right?
Yeah. If there are two candidate keys, then combination will be super key.
Okay.
So this is basically what, yeah. So we'll try to solve this question. It's from mock test only, mock test 2. Okay, solutions are already present, but we'll try to solve this question. So here you can see we have a relation R, V, W, X, Y, Z. We are given relation with the following FDs. So FDs are given to us. We need to find out the candidate key here. Okay. So first we'll go with our trick. We'll see which attribute are present, are not present on the right hand side of FD. So W is present, Z is present, V is present, right? It means what? X and Y is not present. So X and Y must be a part of candidate key. So first I have to check whether X and Y is candidate key or not. So if I take the closure of X and Y, so from X and Y. So what I can get from X and Y here, let's see.
Z and V. Oh, sorry, Z.
No. Here you can see V determine W, WX determine Z, YZ determine V here. But here we just have X and Y.
Nothing.
So XY is not determining anything, only XY. It means what? XY is not a candidate key. Then I have to check the combination of XY with V, XY with W, XY with Z here. All the remaining attributes, I have to check the combination with that. Let's see which are the candidate key now. What about XYV? If I take the closure of XYV, what I can get? From V, I can get W. From W and X, I can get Z. So that's it. All attributes are present. It's so XYV is basically candidate key. What about XYW?
Sir, can we take the WX in the first one?
W?
WX is equals to Z.
WX.
Yes, sir.
No,
And
if you
in the first one XYV, we took the WX. We put the Z on that place.
yeah, so here it's a set. So here, in which order you are putting that will not matter. Okay. So
Okay.
here, if XYV, so we'll write XYV because it's determine XYV. But from V, I'm getting W here, so I'm writing W here. Now from X or from Y or from V or from W or combination of any four attribute, what I can get. So you can see W is present, X is also present. So WX is present inside the closure. From WX, I can get Z here. That's why I have added the Z here like that. Okay.
Okay, sir.
Now, if you look at X, Y, W here, so X, Y, W will be there. Again, from X or Y or from W, can we get anything? But here we have WX, right? In the closure. So from WX, what we can get? Z here. But we have Y, we have Z as well. So from YZ, what we can get? V also. It means all the attributes. So X, Y, W is also key. What about X, Y, Z? Let's check for this as well. X, Y, Z. So from YZ, what I can get?
V
V
and V to
and
W.
W. So again, we have a R. So all these three are my candidate key. So if you can see only two are present. So here B and C are my candidate key here. And but X, Y, Z is also my candidate key here. Okay. So this is how we can find out the candidate key. Okay. So we have to
Sir,
check for a combination of all other attribute if this is not a candidate key. Yes.
won't we check for for two attributes we didn't get any candidate, so we increased one more attribute and we started checking for three attributes closure, right? So
Yeah.
won't we go for four attributes like X, Y, V, and W and check its closure whether it will suffice for candidate key?
No, if we know that X, Y, V is basically candidate key. So if I take a combination of X, Y with any other attribute, that is basically my super key.
Super key, okay.
Right? So if I already know that X, Y, V is basically candidate key, so there is no need to take the combination here.
Further unique combinations aren't there, so
Yes.
Means we have to find minimal.
Minimal only, yeah. Otherwise, that will be a super key, right? So let's say, for example, here inside the XY, we just got XY here. But if I take the closure of XY, I got XYW as well. So anyway, that is not basically my candidate key, right? So in that case, you just need to take the combination of XY with the attribute which are not present inside the closure. That is basically V and Z only. Because if I take the combination of XY with W, anyway, I am going to get the same closure here, right? Like that. So if inside the closure, if you are not getting any other attribute, so that attribute we have to take the combination with those things. Okay. So because anyway, if I take the combination of any one of this, so I'm going to get this closure only. Okay. So just take the combination of XY with the attribute which are not present inside the closure. That we have to check. Okay. So this is about the candidate key. We'll discuss because in most of the questions we have to find out the candidate key. Okay. We'll discuss in further here. Okay. So a simple question. Let's try to see whether we determine WX exists in this table. Not exist, but which will violate? Which row will violate? R1, R2, R3. Tell me which will violate this first option here. So we have a table. We need to check which FDs does not hold on the given table. Is this holding on the given table?
Why is it missing?
No, on this table, whether we determine WX, is this true?
Yes.
So how to solve this kind of question?
B9, 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 and we have A only for X.
So here, for every unique left-hand side value, there must be a unique right-hand side value here. So if I say B, if B is determining what? Wx. If B is determining 9, 8, then in all the tables, B should determine 9, 8 only. If you look at, just check for B, again 9, 8, B, 9, 8, this is fine. And here we just have one tuple, so 9 determine B8, that is fine. So here we determine Wx. We have to check for a combination of Wx here. Okay, so combination must be determined by this particular V here. We usually determine this combination. Okay, it is possible that B can determine 8, 9, but that is not applicable here. If B is determining 9, 8, so it should determine 9, 8 only. Okay, what about Y, Z, X?
But
What
in
about
second row,
second row? Left hand side is different, right? It's 9 determining B8. That is fine. In another, in entire table, 9 should determine B8 only. Okay. So for every unique left hand side value,
Shall we decompose the right hand side and look for it?
That also you can do, but here we don't need to decompose. You can directly check whether the V uniquely determines Wx or not. Okay. What about Yz determine X? Is this true? Yz, combination of Yz we have to take. So Yz 7, 5 determining 8, 7, 1, 2, 2, 3, 6. But anyway, all combination on the left hand side is unique. So anyway, that will be applicable here. Okay. What about X determine YZ? X, YZ?
Not determining.
All are different.
Yeah. So if you see 8 determining 7, 5, 8 is also determining 7, 1. That is not possible, right? So option C is not correct. So when I say uniquely determines means what? Your roll number is there, right? Roll number determining name, right? So your roll number uniquely determines your name. It's not like that 21 F1 will have the name Rajesh and again 21 F1 will have the name Suresh, right? It is not possible, right? So this determined uniquely here like that. Okay, so left hand side uniquely determines right hand side. This is how FD works. So if you look at option number C, not correct. What about D? WY determines Z. Again, WY determining Z.
Determines.
All different combinations.
All are different combinations. So anyway, you need to determine this one. Okay. So simple FDs you can check like that.
Sir, first option, could you explain it again?
Yeah. So we determine WX here, right? So here you can see B determining WX. So B determine 9, 8 here. And here you can see B determine 9, 8, B determine 9, 8. So B should uniquely determine the right hand side value here. If I say B determine 9, 9, then it will not hold true because B is also determining 9, 8, B is also determining 9, 9. That is not correct here, right? Okay. So it should be a unique determine a thing.
So you can say
similar to 1-1 relation.
Because you can say roll number determining name. So roll number is uniquely determine your name. That's it, right? Remember this. Now, if you look at this FDs, we can apply a few Armstrong axioms as well. So first we have decomposition rule. Decomposition rule. Now, if I say we determine Wx, it means what? We determine W and we determine X as well. So we can apply decomposition rule on the right hand side, but not on left hand side. If YZ determines X, it does not mean that Y determine X or Z determine X. No, this is not correct. We apply decomposition rule to only right hand side here, like that. Okay, so don't apply decomposition rule to the left hand side. That is not applicable. Similarly, union rule as well. So if I know we determine W, we determine X, so I can do like this. We determine WX. That is basically union rule here. Okay, so remember this one. And also, if A determines B, it means what? CA, I can put any attribute on the side along with the A, that will uniquely determine B only. Because if A is unique here, if I can put any attribute here, A, B, C, D, E, F, G, anything, combination will be always unique because A is unique there, right? So I can do like that.
This is the augmentation axiom.
augmentation. So if A determine B, so I can augment C on both the side like that. So I can see CA determine B like that. Okay. And we have one more thing, transitivity. If yes,
what if
question.
A is not unique and it determines B?
If A is not unique, determines B. So that FD will not hold true, right? We are saying A determines B holds true. Then we can augment any attribute on the left hand side here.
Okay.
Yeah. Okay. So this is the case here about, and then we have one more transitive dependency. So if A determines B and B determines C, so by transitivity we can say A determines C as well. Okay. These are the few rules.
What was the previous person asking, sir? I couldn't understand.
No, she is asking if A is not uniquely determining B. So in that case, this FD will not hold true, right? So we are saying if A determines B is there, so I can augment any attribute on the left hand side. That is also applicable. Okay.
Yes.
And this is about the keys and how to find out a candidate key. Now tell me what are prime attribute and non-prime attribute?
Those are part of candidate key. We call them as prime, and those are not. We are non-prime.
Yeah. The attribute which are part of candidate keys. The attribute which are part of candidate key, that is basically my prime attribute, and remaining attributes are my non-prime attributes. Remaining are non-prime attributes. So if I say I have a relation R having A, B, C, D, E as my relation, and let's say for example, candidate key is basically A, B, and C, D. It means what? Prime attributes are A, B, C, and D. And non-prime attribute is basically what? Remaining one, that is E here. Okay, like that. So attribute which are part of candidate key, that is basically prime attribute. Otherwise, all remaining will be my non-prime attribute. Okay. So this is about the
So
keys
it means
here.
prime attributes are super keys also.
No, no. So if AB is basically a key, right? It's a candidate key. A and B are prime attribute. It doesn't mean that A is a key here, right? AB is basically a key. So A and B are prime attribute because those attributes are part of candidate key. But A and B individually is not a key here. Okay. So we are simply saying attribute which are part of candidate key. That's it. Those are my prime attribute. Okay. It doesn't mean that A or B will be my key. It can be possible, but for this case, it is not correct. Okay. Okay. So we have discussed this thing. Now we have left with decomposition here. Now let's try to solve one decomposition question here. Okay. So let's say, for example, I have a relation R. I want to decompose that into R1 and R2 here. R1 and R2. Okay. So what is lossless decomposition? Lossless decomposition means what? If I join these two relation back, I should get the original relation back here like that. This is what lossless decomposition is. After joining relation, two relation, if I am not getting the original relation back, that is basically my lossy decomposition here. Okay. So there are few conditions to check whether the decomposition is lossy or lossless. So the condition for lossless decomposition here, yes, anyone? Condition?
R1 union
of
R2
R1
should
and
be
R2 gives
R1 intersection R2 not
R1
empty.
not
R1
null.
should not
union
empty.
R2 is equal to R.
R1
R1 intersection R2 and
Not
equal
not
5.
R1
R1
intersection
intersection R2 is equal to either R1
R1,
or
R2.
R2.
Yes. So here we have first condition. So R1 union R2 should be equals to R. It means what? If R is A, B, C, D, E. So here R is A, B, C, and here R is, let's say for R2 is basically what my D, E, right? So R1 union R2 is covering my all the attributes here. You can see A, B, C, and then D, E. This is fine. Okay, this is what this first condition ensures. What about the second condition? R1 intersection R2 should not be empty set. Empty set means what? There must be some common attribute. There must be
But
some
here
common
it is
attribute.
empty.
Yeah. Some common attribute here. So we have to add some common attribute between R1 and R2. But which common attribute? You can see the common attribute, which is basically will give me either R1 or R2. Okay. It means what? That common attribute must be a key of either R1 or R2. Can we say like this?
Yes, sir.
Yeah. So we have to add an attribute such that it should be a key of either R1 or R2 here. Okay, like that. So if all the conditions are true, then we can say our decomposition is lossless decomposition here. Okay. So let's see how to apply this particular.
Sir, can you please tell what will we do when we decompose the relation into 3 tables?
Yeah. So if I decompose the relation, let's see here we have 4 decomposition, right? So we are decomposing the relation R into 3, then 4, then 5 like that. And how to check in that particular case? Okay. So let's go with the first option here. So first read the question, consider relation R. So R is given to us, having FD. So FD is given to us. Then which among the following is a lossless decomposition here? So in this case, what we need to do? Go option wise. What about the first option here? So here we have 3 decomposition, but whatever the condition we have checked, it is just for 2 relations here, right? So this condition is basically what? For what? When we are decomposing R into R1 and R2, we always decompose R into R1 and R2 first, and then we check whether R1 or R2 is the required form or not. If not, then we decompose further R2 into R21 and R22 like that. It's not like that we're decomposing R into R1, R2, R3, R4 directly. No. First, we always decompose R into 2 decomposition. Then we check for required normal form. If it is satisfying, then it's fine. Otherwise, we again decompose this relation into R1, R2 like that. So this will be my R1, this will be my R2, this will be my R3 like that. So we always decompose one relation into a 2 sub-relations. That's why we are dealing with this particular conditions. But if I want to take backwards here, in that case, what I need to do, so this is for decomposition purpose, how we decompose a relation into a required normal form. For that purpose, we can apply these rules. But here what we are checking, whether decomposition is lossless or not. So in that case, what we need to do, take any 2 decomposed relation such that there must be some common attribute. So we can take R1, R2 because no, there is no common attribute. So I can take R1 and R3 because I is R1, R3 we can take because I is common, or R2 we cannot take anyway because so let's take R1 and R3 first. So if I take R1 union R3, right? Okay. So first condition is that R1 union R2 union till Rn. It should give me all the attributes here. So it doesn't matter how many decomposition we are doing here. So if I take a union of all such relation here, R1 union R2 union R3, in this case R4, R5, that should give me all the attributes in the relation R here. This is the first thing. So let's check here for the first condition here, R1 union R2 union R3. Tell me, are we getting all the relations here?
No.
Yes.
Yes. Now, if this is clear, then go for second thing. Take any 2 decomposed relation such that there must be some common attribute. So R1 intersection R3. What is common attribute here?
I.
Yeah, I. So from I, can I get R1 or R3? That we have to check. But how we can check? Take the closure of I here. So from I, what we are getting? Nothing. Only I. Right? Only I, right? Yeah. It means what? I cannot join this 2 decomposition. Anyway, R2, we don't have any common attribute with R1 or R3, so that's it. Option A is a lossy decomposition here. Okay. Now, similarly, I can check. Yes.
What did you check by taking the closure?
Whether if I take the closure of I, it should give me either R1 or R3. So if you look at the condition here, that common attribute must give me either R1 or R2. So here we are set R1, R2, but here we are dealing with R1, R3. If the closure of I is giving me all the attributes in R1 or R3, then we can join R1, 3 here. Okay.
And sir, actually, R1 intersection R3 when I join, and I cannot join the R2 again. So second condition it's failed. So
No, sorry. Can you repeat?
the R1 intersection R3. So
Hmm.
I'll be getting A, B, C, I, H, G, and I cannot again intersection with the R2.
Yeah. So R1 intersection R3 is basically only I is common here, right?
Yeah.
So from
After that,
I
I
will,
cannot join with the
yeah. After
R2
that we
again.
cannot join. Yeah.
That
We'll
is a
we'll
condition.
we'll check with option number 2 here. See, again, if you look at
Means,
R1,
the common attribute which we are finding, that should be the candidate key, right?
candidate key of either R1 or R3.
Yes.
Okay. It can be a super key as well. It's just a key. That's it. Okay. So if you look at the option number 2 here, we have R1 union R2 union R3 union R4 is giving me all the attributes. So first condition is check. Then go for second condition. Second condition is what? Take any two decomposed relations such that there must be some common attribute. Now, can I take R1 R2? No. R1 R3? No. R1 R4? No. So basically I can take R2 and R4, right?
Yes.
So if I take R2 intersection R4, what I'm getting? D here. Now whether from D can I get R2 or R4? Tell me, what's the closure of D?
R4 can be.
IJ.
Yes, sir.
So it
R4.
satisfies R4.
Yeah. So from D I can get Dij. It means it's equivalent to R4. So my required condition is getting satisfied. Now what does this mean? I have taken two decomposed relation R2, R4, and there's some common attribute, and that common attribute is basically a key of either R2 or R4. It means that I can join this R2 and R4. I can join this R2 and R4 here. Okay. So what I can say R24 as equals to R2 union R4. That is basically what I am going to get D, E, F, I, J. Okay. So now I have joined R24. Now I have to check R24 with R1 and R3 now. Okay. Now which will go first? Which common attribute is present in R1 or R3 from R24?
Nothing, sir.
Nothing.
No. So I cannot take any combination here. So again, this is basically a lossy decomposition. Okay.
That's what
Now let's
that's what
check.
I said in the first example. It should actually null. The intersection is null.
Intersection is null.
Yes.
Yeah. So what about option number C here? Again, R1 union R2 union R3 R4 R5 is basically giving me all the attributes. Now, can I take R1 R2 or R1, or which combination we should take first? You need to decompose relation.
R1, R2. It will give our intersection A.
Yeah. So let's take R1 intersection R2. We have A in common. But if I take a closure of A, what we are going to get?
DE.
ADE. That is basically what?
R2.
R2. It means I can join this relation. So I am going to get R12 such that R1 union R2 after joining, the attributes will be what? A, B, C, D, E. That's it. Now we have R12. I have joined R12. Now can I join R12 with R3, R4, R5, or can I join R4, R5, R3, R4, R5? Anything we can go.
R12 will join with R3. B will intersection.
Yeah. So that also we can do. We can also go for R3, R4 also. Okay. Let's go with R3, R4. Let's see what happens. If I take R3 intersection R4, what is the common attribute here?
F.
F. But from closure of F, what we are going to get? FGH. What is that? R4.
R4.
It means what? I can join this. So again, I can say R3, 4. I can join. That is basically R3 union R4 is equals to what? BFGH. Now I have three relations now. R12, R3, 4, and R5 here. Now which two I have to take?
R12 and R5.
R12, R5.
R12 with R5 also we can go because D is common, and R34 D R5 any common? No. R34 R12 also we can go because B is common, right?
Yes, sir.
So let's go with R12 intersection R34. What is here? B is common, right?
Sir,
Now
from over here,
yes.
R34 and R5 are not having common elements, right?
R3 and R5.
Yeah, R34 and R5. Yeah, yeah. So like can can we say it is a lossy composition because like they're not having common?
No, we cannot say like it. We have to check one thing here, everything. Okay. We have to check all the possible combinations here. Okay. So you can see here R1 to intersection R34 here. So if you look at here, yeah, what is common? B, right? So if I take the closure of B, what am I getting R12 or R34? From B, I can get F. From F, I can get GH.
GH.
It means what? I am getting R34, right?
Yeah.
So it means what? I can join R12 with R34. So R1234 is basically what? Again, A, B, C, D, E, F, G, H here. Right? Now what is remaining? R5, R1, 2, 3, 4 intersection R5. D is common. If I take the closure of D, what is here? Dij. Again, we are getting R5 here.
R5.
Yeah. So it means what? R5. It means what? I can join R1, 2, 3, 4 with R5 so that I can get R1, 2, 3, 4, 5. That is basically equals to R here. So this is basically a lossless decomposition here. Okay. So this is how you need to proceed in this particular case. Take any two decomposition such that there must be some common attribute. And if after doing all these things, R1, 2, 3, 4, and if there is no common attribute in R5 with R1, 2, 3, 4, that will be lossy. Or if this common attribute, let's say for example, here I have added I here and here, okay, instead of D. So if I is common attribute here, but from I am not going to get R1, 2, 3, 4 or R5. In that case, that is also a lossy decomposition. Okay. So we should be able to join all the decomposed relation to get the original relation back. That is what a lossless decomposition here.
So there's a question. So when you joined 1, 2 and R12 intersection R34, the next two attribute we have to combine R1, 2, 3, 4 and this R5, 6 like that, right?
Yes. So we can also go with R12 that intersection R3 also because B is common and from B I can get R3. So that will be R123. Now R123 check with R4 also. So you can go in that order also. No worries. Okay. So the main thing is at the last we should be able to get R1, 2, 3, 4, 5 like that.
So
Yes.
sir, once it's joined, we have to take that as union and again check with other like that, right?
Yes, yes.
That's awesome.
So what we are doing here, we have yes, go ahead.
Sir, I got disconnected. Sorry for asking this again. Since if you go to that example, R1 and R5 are not having any common attributes. Like how can we say that this going to be lossless decomposition if they are R1 and R5? If you go initially, we find no common attribute is there. So like we tend to say that this might be lossy decomposition, right?
No, no. You have to check. You have to take two decompositions such that there must be some common attribute. So I would take either with R1, R2 or R1, R3. So there must be some common attribute. That thing you have to check. Okay. It's not like that I cannot join R1, R5 directly, but if I join R1, 2, 3, then I can join with R5. Okay.
Okay. Sir.
So you have to check all the things here. So if you look at here, if I decompose this into R1, R2, R3, so it is possible that first I need to join R2 with R4, that I will get R2, 4. Then I need to join R2, 4 with R5 to get R2, 5, right? R2, 4, 5. Then I will join R1 with 3 if I can join. So R1, 3. Then again I can join this one to get R1, 2, 3, 4, 5 like that. If it is possible that I cannot join R1, R5 directly, but I can join R1, 2 with R5 like that.
Okay, sir.
So if you, yes, go ahead.
No, sir, please go ahead.
Yeah. So if you observe, if you watch the lectures in one of the slides, what professor has discussed, even though if I say all these things are you getting to a lossy decomposition, but if I add one more key here, R5, such that it is a candidate key of original relation. Or what I am saying, I am adding R5 such that it's a candidate key of original relation, then entire decomposition becomes a lossless decomposition here. Okay. So because if any one of the relation, if any one of the decomposed relation is a candidate key of R, I am saying candidate key, not super key. If any one of the relation is basically a candidate key of that particular original table R, then that entire decomposition will be a lossless decomposition here. Okay. So in one of the lectures, we have discussed that because we are not getting a lossless decomposition. So we have added one new table such that it's a key of original table. Okay. So if you look at here, what will be the key? C is present, F is present, IJ is present, DE is present, GH is present here, right? Only AB is not present on the right hand side of any functional dependency. It means what? AB must be a part of candidate key. So if I take the closure of EB here, so from AB I can get A, B, C. From C, from A I can get DE as well. From B I can get F as well. From F I can get GH as well. From D I can get IJ as well. So AB is a candidate key here, right? So
Yes.
yeah, if AB is a candidate key and if I add EB here as my R5, or let's say here if I add R for EB here, now let's see what happens because this was also lossless. So here if I take, let's say for example, any common attribute, yeah. Let's take R1 with R4. So I can join R1, R4 because anyway AB is the key. Okay, so again, yeah. Okay, so here that is not a thing. Okay, so I guess that's the different condition for a normal forms. Okay, when every relation is the required normal forms, let's say every relation is in 3NF, 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 and that in that case decomposition is not lossless. In that case, we can add the key. Yeah, sorry, it's not for a direct decomposition. It's for a related to normal forms. So please check in one of the slide. We have discussed that. Okay, it's not applicable to simply checking for decomposition. Okay.
So if you talk about super key, then here can we say ABC is a super key, ABF is a super key?
Yes, if AB is my candidate key, so you can take combination of AB with any other attribute that will be my super key. AB is also super key. Okay.
Yes.
Yeah. Okay. So we have discussed this one. Then next is basically in week 5 we have dependency preserving.
Sir.
Okay. Yes.
Sir, in prime attributes, once could you go to that page once?
Prime attribute.
Yes, sir.
Okay. Yeah, you can ask the question. Yeah.
Sir, if AB is a candidate key, like if A, B, not A and B, then individual A and individual B are not prime attributes, right? AB.
No, A and B are prime attributes here. The attribute which are part of candidate key that are basically prime attribute. Okay. So just A is also prime, B is also prime here. We're only discussing about the attributes here, prime attribute, individual. If that individual attribute is part of a candidate key, that's it. Okay, if A, B, C is the key, it means what? A and B are my, A and B and C are my prime attribute. Remaining are my non-prime attribute.
Sir, if they're independent, then also they're prime. Obviously, they are prime attributes, right?
Yes,
Like,
yes. If it is a part of candidate key, that's a prime attribute. That's
okay,
it.
sir. Okay, got it.
Sir, like one clarification, like in 2NF, like you mentioned that left-hand side should be a part of candidate key, right? Along with partial dependencies. So if we have along with the prime attribute, some other non-prime attribute also, and that determines a non-prime attribute, will we still take it as a partial dependency?
No, we'll discuss that in normal form. So prime attribute determine non-prime attribute. This is what we are saying, right?
Yeah. In left-hand side, we have prime attribute and non-prime attribute also.
Prime attribute and non-prime attribute.
And this determines a non-prime attribute.
Okay. So here in that case, yes, that will be also a partial dependency, we can say. Yes. If it is on this particular side, then there is no issue.
Yeah,
On this side, it's also partial dependency. If it is a prime attribute, not the key.
Okay, got it.
Yeah. Okay, we'll see about dependency preserving. That topic is remaining. Let's see this question here. Okay, so lossless and dependency preserving, yeah, both are covered. Okay, so here we have question number 9 from mock test. So we have a relation R, we have a bike name BN, bike model BM, bike engine number BE. We have FD, bike and determines bike model. Then we have bike model determines bike engine. Then we have bike engine determines bike name here. Okay, these three FDs are given to us. R is decomposed into this one. Now tell me, it's a lossy or lossless decomposition?
Lossless.
So R1 union R2 is giving me R. So all attributes are covered. R1 intersection R2 is basically what? Bike model. And if I take the closure of bike model, what I am going to get? Bike model.
Bike engine number and bike name.
Yeah, so R2 basically, right? So this is basically a lossless decomposition. This is fine. But what about the dependency preserving? How to check for dependency preserving? Yes, anyone?
It's like bike name is dependent on bike model, or R1 is
dependency preserving. So here you have decomposed R1 and R2 like that. Okay. Now first what you need to do, find out F1 and F2. So F1 and F2 are the functional dependency set applicable to R1. F2 is basically functional dependency set applicable to R2 like that. So if I see here, when I say all FDs applicable to R1, it means what? You can see bike name and bike model here we have, right? So from bike name, what I can determine? So from bike model, what I can determine? If you observe here, we have this FDs directly. So I can add bike name determine bike model. But that's it. We just have two attributes here. But what about bike model? Can bike model determine bike name here?
No, sir.
So we have to check. So we have to find out all the applicable functional dependencies to decompose relation from the original FDs here, right? So if I take a closure of bike model based on the original FDs here, what I'm going to get? Bike model, bike engine number, and from engine number I'm going to get bike name here, right?
Yes.
It means what? Bike model can determine bike name, right?
Yes.
So we have to add that FD as well here. Okay. So that is what I have said, applicable all the functional dependencies to R1 based on the parent FD here. Okay. So if we have this attribute here, if we have one more attribute, we have to find out whether that attribute can determine other attribute by taking the closure of based on the parent FD here. Okay. So there is one tutorial based on the dependency preserving. So please to watch that tutorial. In that we have discussed different examples like that. Okay.
So where given in portal about?
Portal only you can see, as a part of course only. Yeah.
So once could you please explain dependency and not dependency, how to check?
Sir,
okay.
Only like
yes.
Like by the dynamic connectivity lecture is there, or where we have to see?
No, in the week 5 only you can see few tutorials in the portal itself.
Okay, content lecture like.
Yeah, content. Yeah.
Okay.
Okay, so here first you just write down the function dependency directly from the FDs here. So here I know bike name is present, bike model is present. So this I can directly write it down here. But from bike model, can I get bike name as well? Okay, so that is what you need to think. So that we have to check. So I have taken the closure of bike model based on the parent FDs here. And I got this closure, bike model, bike engine number, and from bike engine number, I'm getting bike name. It means what? Bike model can determine bike name as well. Okay. If
like using transitive.
Transitive dependency, yes. So A determines B, here B determines C. So I can say A determines C, right?
Yes, sir.
Yeah. So you can apply those rules, but the best way is that take the closure and see whether we are getting that attribute in the closure itself or not. Okay. So all the rules will be applicable once you take the closure. No need to check for every rule here. So if I take the closure of any attribute, let's say for example, A, B here, and I'm getting this one, A, B, C, D, E, Z. It means what? AB can determine C, AB can determine D, AB can determine EZ, like that. Okay. So if AB closure, if we got this attribute, it means what? AB can determine all the attributes here. Okay. You
So
can see it.
if bike model is not dependent on bike name, then it was not dependency preserving.
No, we'll see. We cannot do verify like that. We have to find out all the FDs applicable to R1, R2, and then again we have to take the union of F1 and F2 here. There's some
Yes.
process. We'll discuss that. So
Sir,
first,
for the functional dependency of AB, we can't say that A determine C directly. We have to say AB determine C.
yes, because in the AB closure we are getting all this attribute, not A closure, right? So AB can determine C, D, E, Z, like that. Okay, and then by decomposition you can apply all these things.
Okay, sir.
Okay. Now see, first we need to find out all the FDs applicable to R1 and R2. So this is what we have done because we just have two attributes. So that's it. What about F2 here? Bike model, bike engine number. So I can write down directly bike model and bike engine number. Now whether bike engine number determines a bike model, can you check? How we can check? Take
Yes.
the closure of bike engine based on the parent
Yes.
FD here. So from BE, I can get what? Bike
BN.
bike name, right? And from bike
Yes.
name, I can get bike model. So you can see I am getting BM as well. So BE also determine BM. That's it. So we got F1 and F2. Now in the third step, what we need to do? So the first step, write down R1, R2. Second step, find out all the applicable functional dependencies to F1 and F2. Now consider F dash such that F1 union F2. It must be a collection of all the FDs, like what we have find out, F1 and F2 here. Okay. And then which dependency is not preserved directly, we have to check for that. So if you observe here, bike name, bike model, bike name, bike model is already preserved. Bike model, bike engine number, BE, BMB, no, BMB, here you can see bike model, bike engine number is also preserved. What about bike engine number, bike name? BEBN is preserved or not directly? No, right? Because bike engine is in the R2, bike name is R1, right? So for this such cases, we have to check whether it's preserved or not. Otherwise, these two already preserved in the decomposition. But this is directly not preserved. So for this only, we have to check all these things. Now, this is remaining. So we have to check whether BE determines BN or not. But how we can check that? Take the closure of BE based on F dash here. That is basically F1 union F2. So all the FDs will be there. So if I take the closure of BE based on F dash, what I can get? So from BE, I can get BM. But from BM, I can get BN. It means what? BE, I can get BN, right? Right?
Yes.
So you can see by using this FDs, F dash equals to F1 union F2, I can determine the BE determine BN here. So this is preserved. That's why it is all as well as dependency preserving. Okay. So it's not like that directly you can say if attributes is present, this is preserved, this is preserved. These attributes are not present because one is present in this relation, another in this relation, so it cannot be preserved. No, you have to check for these things. This is a process that you have to check. Okay. Otherwise, if you directly already preserved, then no need to check. Okay.
Can you explain once again how it dependency preserving?
Yeah. So if we have three FDs here, right? So first one is getting preserved in R1 because we have bike name and bike model, bike name, bike model, right? Second one is getting preserved in R2, bike model and bike engine number. Third one is not getting preserved because I cannot add this FD in either R1 or R2 because bike engine number is present in R2 and bike name is present in R1. So where I can add this one, I cannot add this FD directly. So how we can check whether it's preserved or not? So for that purpose, we need to find out F1, F2. That is basically set of all the FDs applicable to R1 and R2, and then take F2, F dash equals to F1 union F2. Okay, and then take the closure of that remaining FDs based on F dash here and see whether we can preserve that FD or not. It's a process that we need to follow. If you look at the slides also, in that we have discussed one examples. Let me, sorry, DPM slides. Just a second. Here, do we have this? Let me check. Week 6. You can see this example, right? It's from slides only. So here we already find out all the applicable FDs like that, F1, F2, F3. Then we have considered F dash equals to like this. Then we are checking for this one because D and A is not present. D is in R3, A is in R1. So I cannot say that D determine A preserved or not. So for that, we have to follow all this process. And then we can say D determines A is preserved because from F dash here. Okay, so please go through these tutorials. We have a tutorial as well as these examples. We have one more example in the slides, so you can just go through that. Okay, so this is regarding the dependency of preserving here. So here we have covered week 5. Anyone, any doubt in week 5? FD, closure, keys, prime attribute, non-prime attribute, number of super keys, decomposition, dependency preserving. All concepts are important and applicable to normalization here. Any doubt in any one of this particular concept?
No, sir.
There
Okay,
is
great.
PYQ for which I am getting the wrong answer, which is based on the functional dependency and lossy. Should I ask right now
No.
or the last?
First, let me complete the normalization form, then you can ask your question. Okay. Okay. So first, we'll discuss about the week 6 now, that is normalization here. So entire week 6 deals with what normal forms? We have 1NF. Now tell me how to check whether relation R is in 1NF or not. How to check? Yes, anyone?
No multivalued attribute.
No multi-valued attribute. Now, what do you mean by multi-valued attribute here?
The
attribute should have only one value.
Yeah. So if you look at a particular column here, let's say for example, phone number. So it should have only one phone number, 999 like that. Okay. Not, we cannot put two phone numbers here, 99 or 839 like that. Okay. If we put two phone numbers in a one particular field, that is basically MVA. So we represent MVA in ER diagram by which symbol? Yes.
Double arrow.
Double ellipse like that. This is symbol for MVA in the ER diagram. Okay. If there is no multi-valued attribute, so we can say it is in 1NF, or we can say domain is atomic, or we can say domain is atomic. Okay. If in the question it is mentioned that all attributes like there is no MVA, or we can say domain is atomic, it means it is in 1NF. Even if it is not mentioned, you have to assume that relation is in 1NF. So always assume R is in 1NF. Okay. Now what about 2NF? What's the condition for 2NF?
No partial dependency.
No partial dependency. Now what do you mean by partial dependency here?
Part of candidate key should not determine the non-prime attribute.
Yeah. Subset of candidate key determining non-prime attribute. This is not allowed in 2NF. Okay. If I say AB is my basically candidate key and C, D, E are my non-prime attribute. So if A determines C is present, or if A determines D is present, it means what? Subset of candidate key determining non-prime attribute. This is not allowed. This is partial dependency here. Here also partial dependency. So here, just remember this condition: subset of candidate key determining non-prime attribute. What about 3NF?
Like our prime attributes should not determine non-prime attributes.
Yeah, but that prime attribute should not be a key. Okay. So if I say AB is basically a key, but it is a prime attribute also, right? If I say A is basically my prime attribute as well as the key, right? If A is a key and if A determines C, this is fine. Okay, because A is the key here. So left hand side should not be key here. Okay, so subset of candidate key here. But only A is a key here, and if A determining C, that is fine here. Okay. What about 3NF? What is the condition
No
for 3NF?
transitive dependency. No transitive.
No transitive dependency.
Non-prime attribute should not determine non-prime attribute.
Yeah. So NPA determining NPA is not allowed in 3NF. So NPA determining NPA is not allowed in 3NF. What about BCNF?
Each functional dependency from alpha to beta alpha should be a super.
Yeah. So left hand side of every FD must be a key. Can we select that?
Yes, sir.
Sir.
Yeah. So left hand side of every functional dependency must be a key. What about 4NF?
No
There should
multivalued.
not be multi-value dependencies.
No multi-value dependency, MVD. So we represent MVD by double arrow like this. A multi-determine B. So we'll discuss this concept later, right? But in order to be in 4NF, it should be in BCNF first, but it should be in 3NF first, it should be in 2NF first, it should be 1NF first, like that. If it is not in 3NF, it means it is not in BCNF as well as 4NF. Okay, like that. So first we have to check whether 3NF, whether the relation is in 2NF, then only we can check for a 3NF condition here, like that. That's why we can say it's a more stricter form of normal forms here. So anyone, any doubt here about these conditions? You have to remember these conditions for each normal form. That's it. And rest is just how you find out the candidate key and prime attribute, non-prime attribute. That's it. So these conditions are very, very important. Now let's try to solve few questions. Okay. So here you can see question number 2. We have a relation R, domain is only atomic values. It means R is in 1NF. Which set of FDs satisfy R such that R is in BCNF? So we have to find out the functional dependency set such that R is in BCNF here. So what are the condition for BCNF? Left hand side must be a key of every FD here. So if I look at this thing, first option here, how to proceed? Yes, anyone? How to check this option?
First find the candidate key.
Find whether ABC is a key or not.
So first we have to find out the candidate key here. Then only we can check if left hand side is key or not. Or directly can we check left hand side is key or not?
Yes, sir, it's key.
So what we need to do in the case of BCNF? Take the closure of left hand side of FDs here. Right? If it's giving me all the attribute, it means it is a key here. Right? So if I take the closure of ABC here, am I getting all the attributes here?
Yes, sir.
ABC, from ABC I can get a D. Anyway, AD will give me BC. So ABC is basically key. What about AD? If I take the closure of AD, am I getting all the attributes?
Yes,
So from
AD,
AD I
BC.
can get BC here directly. Right? So AD, BC. So this both are my key here. Right? So it is basically what? Left hand side of every functional dependency is key. So that is basically in BCNF here. What about option number 2? Is AB is a key? Take the closure of AB.
Yes, sir.
From AB, I can get CD. AB is a key. This is fine. What about CD? Determine B.
No, sir. A is missing.
If I take the closure of CDB, so CDB will be there. A will
A is
be not
missing.
there. So this will violate my FD. What about this one?
Sir, if
This
we
will
take the
missing.
closure of
B is
CD,
missing.
then
B is missing.
CDB, and by D we will get the
Yeah,
A.
yeah. Sorry.
If you take the closure of CD, CDB here, right?
And by
And
D we
from
will
D,
get
get A.
We can
Yes,
get
yes. So we can say CD is also a key, right? This is also fine. What about B determine A? D determine A. Is that a key? Is D is the key? Take the closure of D. From D, I can get A. So from A or from D or from DA, can I get anything? No. So this will violate my BCNF condition here. That's why option B is not correct. Similarly, you can see A will give me A, B, C, D. B will give me B, C, D, A. C will give me D, A, B, C. D will give me again A, B, C, D. So again, it's satisfying. Every left-hand side is
Sir.
basically a key. Yes, any question?
Sir, here in this, these FDs are transitive.
Sorry, this one, second, third option.
Yes, sir. Yes.
So here in the case of FD, we are saying non-prime attribute determine non-prime attribute is transitive dependency here. But here all are the prime attributes. So left hand side is basically a key here in all the case. There is no prime attribute in this particular case. Okay. What about
but in
Sir,
first option,
I didn't get you. Could you please repeat once?
in the case of option number C, right? So you can see all are individual a key. So A, B also key, B is also key, C is also key, D is also key. So all
Okay,
attributes
okay.
are
All
prime
are
attribute
prime.
here. Yeah,
All are
there is no
prime.
non-prime attribute here. So this will not be present, right?
sir, but in first option there is ABC determine D. That means A, B, and C are prime prime attributes.
No, you can see AD is also key, na? Here AD and ABC both are keys. So if you look at the prime attribute, it's simply a part of candidate key. So A, B, C, and from this key, D is also present, right? So prime attribute is simply the attribute which are part of candidate key. That's it. Okay. So here ABC is also key, AD is also key here.
So in BCNF, if there is any prime attribute, then it can be also be in BCNF.
No, so that attribute must be a key here. Left hand side must be a key. So only one condition you have to check: left hand side is key or not. That's it.
Okay, sir. No matter is there any prime attribute or not.
No, no. So on the right hand side, we don't care about the prime attribute, non-prime attribute. If left hand side is the key, that's it.
Okay, sir.
In option 3, you said A. In option 3, you said A, B, C, C and D are all keys. How by looking the FD we can say how it is keys?
Yeah. So if I take the closure of A here, you can see from A I can get B, from B I can get C, from C I can get D, and from D I can get again A. So anyway, all attributes are covered. So A is a key. Again, same process for B as well. From B I can get C, from C I can get D, from D I can get A. So all are present. So B is also key. Similarly for C, similarly for D. So left hand side of every functional dependency is key here.
Okay.
Right? And all the attributes are prime attribute. There is no non-prime attribute. Okay. What about option number D here? Is AB determine D? Is this left hand side is the key? Take the closure of AB. So from AB I can get A, B, D. From D I can get B. From D I can get C. So this is fine. What about D? D is the key.
Yes, sir.
From D I can get B. From D I can get C. From C I can get A. So D is also a key. This is fine. What about this one? Again, D is also a key, right? D determine C, C determine A, D determine B. This is also key. What about C determine A? Is this a key? Is C is a key?
No, sir.
So this will violate my BCNF. So this will violate my BCNF, and here this will violate my BCNF. Okay. So left hand side of every FD must be a key for a BCNF. That's the thing. Okay. So if you will solve few more questions based on FDs. Yes.
All CNF are also in 3NF, right?
All BCNF is in 3NF, 2NF, 1NF as well. Any decomposition here? Okay, so we'll discuss this question only. Let's see. Yeah, this one. It's a simple question. You can see. I will see any question based on the normal forms. Okay, let's try to solve this question here. So here we have a relation R, and we have a FD, and we need to check what is BCNF decomposed to 3NF like that. Okay. Or if R is decomposed to BCNF, all dependencies are preserved. So all the concept will get clear here. Now tell me how to check whether it is in, so already it is in 1NF, how to check for 2NF? Because if it is not in 2NF, then we can decompose. The first we'll check in which normal form this relation is. Tell me in which normal form this relation is. So the first step is find out the candidate key here. So tell me what is the candidate key for this relation R? Yes, anyone? Yeah, what is the key here for this relation? Just try to find out.
Q.
Okay, already it is present here, so we'll see. Okay, so we'll follow our process, that is the attribute which are not on the right hand side of FT. So P is present, M is present, Q is present, and O, all are present here, right? So in this case, what we need to do? Find out the
Combination.
closure of individual attribute here first. Check for M, check for N, check for O, then P, then Q here. If I take the closure of M, whether M is candidate key or not. So from M I can get NO. So from N I can get P. Now Q is remain. Yeah. So from OP I can get Q. It means what? This is basically a R. So M is candidate key. What about N? This N is candidate key. So from N I can get P. That's it, right? Okay.
Yes, sir.
What about O?
Nothing.
Nothing.
O only.
What about P?
Nothing. I get P
Nothing.
only.
What about Q?
M, Q,
M N O P.
So you can
NO.
see from Q I can get M, but M is already a key, so I can get all the attributes here. You can see from
Okay,
M
okay,
and
yes,
O
yes.
like that. So it is basically equals to R. So my M and Q is basically my candidate key, you can say. But we have just checked for M and Q. The remaining are what? N, O, P. So here we have three attributes, N, O, P. Now we have checked for individual thing here. Now we have to check for combination of this NO, this NP, and then OP. These three combinations are possible here for two attributes. Let's see here. What about NO? Is NO is a key here?
No.
So
Yes.
from N I can get P here. OP, from OP I can get Q, and Q is already a key. So this will give me M as well. So this is basically R. So NO is also a candidate key here. What about NP? Is NP is a candidate key?
No,
From
sir.
NP, I'm going to
No.
NP only. So no.
Yes.
What about OP? Is OP is a candidate key?
No.
Yes, sir. From OP we can get Q, and Q is a candidate key.
Already a key. Yes.
Sorry.
So OP is also my candidate key. So that's it. We have checked for all the possible combinations here. Okay. So that's it. So M, Q, N, O, and OP are my candidate key here. Okay. This is how we can find out candidate keys. So why we have not considered M and Q? Because already it's a candidate key, right? So we have left with remaining attributes. So in that case, we'll take combination of NO, NP, OP. Now let's say, for example, even if I'm taking the NO, NP, OP, will not get any key here. Okay, so not equals to R. In that case, we can go for a combination of three attributes like that. Okay, but anyway, I cannot go for this combination because NO or OP is already a key. This will become a super key here. So here we have just four candidate key. Anyone, any doubt how we got this four candidate key?
No, sir.
So
Yeah,
this is a double combination NOOP. So then finally we are going for the three combination, right? That's the last.
If we did get this NO and OP, so all two combinations are not a key, then we'll go for a combination of three attributes.
NOP.
If it is any one, if it is preserved, then you don't want to go three, right? Only one is enough. For example, if NO is my candidate and OP
Yes,
and
yes.
so we can omit that, right?
Yeah, if NO is my candidate key, OP is not my candidate key, so we cannot go for this combination because anyway that will be a super key, right?
Done.
Yeah. Okay, so these are the candidate key. So what are the prime attributes now?
M N O P Q.
Q and OP.
M, N, O, P, Q. So M, N, O, P, Q. So all attributes are prime attribute here. So there is no non-prime attribute, right? It means what? So
2NF.
Sir,
3NF.
can you explain how to use write P and NP?
So prime attribute, the attribute which are part of candidate key here. So yum is candidate key, I have written. N is part of candidate key. O is part of candidate key, so I have written that. P is also part of candidate key, I have written that. So attribute
Yes,
which
sir,
are
got it.
simply present in the candidate key, that's it. Remaining are my non-prime attribute. There is no
Yes.
remaining attribute here. Now what about this one? N determine P. So first it is already in 1NF, it is in 2NF. Check for 2NF. Do we have partial dependency here?
No, sir.
Yes, sir.
And determine P. But anyway, we don't have any non-prime attribute. So on the right hand side, we don't have non-prime attribute. So 2NF is not possible. 3NF also, NP determine NP is not there. What about BCNF? Let's
If
check for
these are not,
BCNF. Is N is a key?
Yes, sir.
yes,
No, N is not a key here. NO is a key,
Yes,
right?
sir.
yes,
Q is a key.
yes,
Yes.
This is fine. OP is a key. This
yes.
is
No,
fine.
no.
Yeah, yum is a key.
Yes.
This is also fine.
Yeah.
So what is violating my BCNF condition? This one only, right?
NP.
So NP is violating my BCNF condition. It means what? It is not in BCNF. It is in 3NF. So you can see R is in BCNF. No. All dependencies are preserved. No. If R is decomposed into 3NF but not in BCNF, it all dependencies on R cannot be preserved. No, we cannot say that. If you decompose into 3NF, then it will get preserved. R can be decomposed into BCNF such that dependencies are preserved. Now see, if we decompose a relation R till 2NF or 3NF, and if you follow a lossless decomposition thing, so we can guarantee that dependency will get preserved in the case of 2NF, 3NF decomposition. But when you decompose for BCNF, it is possible that all relations will be in BCNF. It is also possible that it is a lossless decomposition, but dependency may not be preserved in that case. Okay. So in the case of BCNF, dependency may or may not be preserved. So we have to check for that. So again, you can see here, so we cannot directly say like this, right? So what about this one? Now for this option to be correct, we have to decompose this relation R into BCNF and then see whether we can decompose, then see whether all the dependencies are preserved or not. So how to decompose the relation now? Tell me.
We have to take closure of N.
We make
Yeah.
the two relations NP in which one attributes are NP and other in the other N and left of attribute.
So see, we know that which FD is violating my BCNF condition. This one, right? So
Yes.
when you want to form a normal form, when you want to decompose the table, first go with the FD which is which is violating my condition here. In the case of 2NF, go for partial dependency. In the case of 3NF, go for transitive dependency here. In this case, it's violating my BCNF condition. So what I will do? I will take the closure of this one and left hand side. What is the N closure here? NP.
NP.
Right? So I will make this relation as R1. Now we have to form R2 such that it should be in lossless decomposition here. So now what we have discussed, those three conditions, now that we have to apply here, right? So R1 union R2 must be equals to R. So first I will add remaining attributes here. That is basically N, M, O, Q. That's it, right? M, O, Q. So these three must be there, M, O, Q. Now, which attribute I have to add in R2 or R1? Tell me.
In R2,
Add N in R2.
Yes.
N
N
in R2.
We can add N in R2. If I add N in R2, then N will be common. And from N, I can get R1 here, right? That will be my lossless decomposition here. So, okay, we have decomposed this R1 as NP, R2 as MOQN. Anyone, any doubt here what we have done? We can also add the key of R2 in R1 as well. So if you look at here, I can also add M here, M and P, and here MOQ. That's it, because M from M I can get R2 as well. We can do that thing as well. Okay.
How will you decide to add N in R2?
Yeah. So here, if you observe here how we decided that, right? So if you look at the FD set here, we just have N and P. So you have to check for FD dependencies also here. Okay. So here we have decomposed this N, right? Based on what? Based on the condition that is violating my dependencies here. What happened?
Okay.
Yeah. So you can see, so that FD which is violating my dependency, right? So I can take the closure of left hand side. And whatever comes inside that closure, that will be my R1 here. That's it. I will not add any other attribute here in the R1. Are you getting what I'm saying?
Okay. Okay.
If this FD is voiding my any normal form condition, I will take the closure of that. Whatever it gets in the closure, that is my R1. That is my one relation. That's it. Remaining all the things, I will add another relation R2 like that. Okay. That's why we are going to add N in R2, not M in R1. Okay.
Then for R2, still we are going to check for the dependency,
Yes.
like which is
Yes.
violating.
So we have to again apply that thing. So here F1 is basically what? Applicable to R1. It is N determine P here. What about F2 here? We need to add all the FDs applicable to R2 based on the parent FD here. So I can say Q determine M, Q and M both are present. M determine E and O both are present, right?
OP determine Q.
No, we cannot add OP determine Q because
Sorry,
here
yeah.
P is
It's
not
not.
present here. Here also O and Q is not present. So this is not getting preserved here, right?
Yeah.
So again, like if you don't add this one, right? So if you see Q is basically key, M is basically key. So Q and M is done. We left with what? ON. If I take the closure of ON based on the parent FD, NO is a key. What are the keys here?
Yes, sir.
If I take the closure of ON, what I'm going to get based on the parent FD? NO.
Only.
No. From N I can get P. So from OP I can get Q, and from Q I can get M. It means from NO I can get QM, right? So it means from NO I can get QM here. And then write like this. Hello.
Yes.
Just a second. Yeah. So we need to find out all the applicable functional dependencies based on the parent FD here, right? So if you look at N can determine O, that's it. And from O, we are not going to get anything. So from O, that's it. Okay. Eraser is not working. Okay, no worries. So here, this is what we got here, right? Now, again, we need to check for this one, whether R1 is in BCNF.
Yes, sir.
Yeah. So any relation having just two attribute, it is in BCNF as well as 4NF. Okay. It is in every normal form, 1NF, 2NF, 3NF, BCNF. Any relation having just two attribute, it is in 4NF. No need to check for anything. Why? Because if I see F here, applicable functional dependencies to this one, there are only two possibilities. Either A can determine B, or B can determine A, or both can be possible, right? In either of the three cases, left hand side will be always the key, right? If only one FD is present, so A is a key. If only this is present, B is a key. If both are present, so both left hand side is a key, right?
Both are keys, sir.
Both are keys, right? So it will satisfy my BCNF condition as well. And by definition, 4NF is not applicable to relation having just two attribute, because for MVD we require at least three attribute in the relation, right? So whenever you see the relation having just two attribute, it is always in 4NF. That's it. Okay. So R1 is already in BCNF as well as 4NF. What about R2 here? Again, Q is basically a key. M is basically a key, right? NO is also basically a key of R2. So this is already also in BCNF. So I can decompose relation R into BCNF. But what about dependency is preserved or not? What about this OP determine Q? If you look at OP determine Q, cannot be preserved here. Okay, so that's why option D is correct here.
Sir, like how can we be sure like this cannot be derived by taking union and all?
Yeah, you can check for that. So that's what we have to do. So if I take F1 union F2 and take the closure of OP based on this one. So if you look at from OP, I'm going to get OP, and from O or from P, do we get anything here? From P, from P can we get En? Let's see. From P can we get En? No, from P only we are getting P here. So already checked. So P is not determining N here. So that's it. From O, can we get any other thing? From O, what we can get? Closure of O is O itself. So that's it. So OP will give me OP only after taking F1 union F2. So that's it. It is not getting preserved here.
Okay.
Okay. So this question is a little bit difficult because you need to decompose that and then check like that. Okay.
Sir, can you tell me how to check for 3NF?
3NF simply first find out candidate key, then find out prime attribute, non-prime attribute. If in the FD, yeah, so either is not working. If in the FD, if NPA determining NPA, if this is present, it means it is violating my 3NF condition. It's a transitive dependency here, right? So if you look at the, let's say for example, here we have yum, then it was which are the FDs? Sorry, which are the keys? Let's say for example, yum q op. Let's say on is not a key here. In that case, my prime attribute will be what? Yum o p q. N is not a key here, a prime part of key, right? But if you look at op here, op is basically a key. But in the FD, if I have p determine n or o determine n, this will violate my what? Which condition? What is this? No, not 3NF. 2NF condition. It's a partial dependency, right? Partial determining non-prime attribute. So that is why it not been 3NF as well. Okay. But if this is also not a key, only yum and q is present, remaining are my non-prime attribute. Okay. And then in that case, P determine O, if we have this FD, again NPA determining NPA will be my transitive dependency. This is not allowed in 3NF. Okay. So the first thing is that you need to find out the candidate key, find out prime attribute, non-prime attribute. So let me write it down somewhere here. So in every normalization, yeah, so in every FD, let me refresh this one. Okay. So what we need to do in the case of normal forms? First step is to find out the candidate key. Find candidate key. Second is basically what? Find out prime attribute and non-prime attribute. This is what you need to do in every normal form question. Find out candidate key, find out prime attribute, non-prime attribute. Now we have few conditions for 1NF. Is no MVA. So we assume that is in 1NF unless it is mentioned in the question that this attribute is having multi attribute, then that will not be in 1NF. Then we have 2NF condition, subset of candidate key determining non-prime attribute. If this is present, it is not in the 2NF. 3NF condition we have to check. If NPA determining NPA, if this is present, then it will violate 3NF condition. This should not allowed. What about BCNF here? Left hand side must be a key. Must be a key of every FD here. Okay. Then we have to check for 4NF. So 4NF deals with MVD. We'll discuss that. But it should be in BCNF first. Right. So first find out the candidate key, find out prime attribute, non-prime attribute, and then check for these conditions. That's it. Okay. So you can try to solve all the questions from week 6 PA and GA based on the normal forms. We have discussed this. So we have discussed almost all the questions from week 5, week 6 from the mock test. So based on the here we'll see. Here we have what? Canonical cover. Okay, we'll discuss. Then we have That's it. Okay, we have this MVD question remaining. We'll discuss MVD concept here. Okay. Okay, any doubt in normal forms 1, 2, BCNF?
Sir,
Yes.
for BCNF, it is not to be not to be in 3NF.
No, it should be in 3NF first for BCNF. It should be in 3NF, 2NF, 1NF like that.
Okay, sir.
Sir, 4NF question come in question exam or not?
Yeah, definitely it will come.
Okay.
Right, so you can see here. So 4NF, it should be in BCNF, but for BC, it should be 3NF, it should be 2NF, it should be 1NF like that. Okay, now let's discuss about MVD concept here. Now, what is MVD? Here we have alpha multi-determine beta. Okay, so if you observe the lectures or the slides, we have discussed few conditions. What is there? You can see, you can check out this particular slides. Okay, we'll see about the 4NF. Yeah. So these are the conditions here. Let's see what is the 4NF here. Let R be a relation schema and let alpha subset of R, beta subset of R. The MVD holds on R if any legal relation R for all pairs of tuple T1 and T2 in R such that T1 alpha is equal to T2 alpha. It means what? To check for MVD to be exist, we should have a two tuples such that left hand side value must be same here. You can see. If we have two tuples T1 and T2 such that left hand side value is same, then we have to check for this conditions here. If this exists, it means what? MVD exists here. Okay, you can see if T1 and T2 here, left hand side is basically a cos. So if left hand side value is same, then we have to check for this condition. It means what? There must exist T3 and T4 such that satisfying this condition. Okay. So either you can remember this thing, all the five conditions, but make sure that once you fix T1, T2, T3, T4, we have to follow this for entire thing here. You cannot change the sequence in between. You can also consider this as T1, this as T2, this as T3, T4. This is also fine. But you have to fix this for checking all the conditions here. Okay. But the best way is that you can see if I say alpha multi-determine beta, it means what? So by definition of MVD, what is MVD here? There must be at least three attributes. There must be at least three attributes. Okay, let's say for example, we have A, we have B, we have C. Out of this, two must be independent here. Two must be independent attribute. Now, what do you understand by independent attribute? Yes, anyone?
Not dependent on any other attribute.
Correct. Yeah. So here, if I say A multi-determine B, so if MVD is present, but there must be two at least independent attribute. It means what? B and C must be independent. It means what? B determines C or C determine B does not applicable here. Okay. If B determines C and C determines B does not exist, then we can say B and C are independent here. Okay. Now let's see here. Now what we have said, if we want to check for any MVA here, MVD here, so just follow one things. Keep the left hand side value same. Okay. So keep the left hand side value fixed. Now take any two tuples such that we have same left hand side value and exchange the beta value. So take any two tuples such that we have same alpha value, that is left hand side value, and exchange, or we can say swap beta values here, right? So after swapping beta values, we will get two new rows. If those rows are already present inside my relation, then we can say MVD exists. If those two rows are not present, then we can say MVD does not exist. So if you observe here, let's try to apply this one. Okay, first, is this clear what I said here? Hello?
No, sir. Can you repeat this one?
Yeah. So here if I have alpha but determine beta, so what I am saying, take any two tuple such that we have same alpha value and then exchange the beta value here. Okay, that's it. So if I want to check for this MVD course and book here, so alpha is my basically course and beta is basically a book here, alpha and beta, right? Now I want to take two tuples such that we have a same alpha value but exchange the beta value. Let's go with this one, this T1 and T2. So I have the same alpha value, but I will exchange the beta value. That is this beta value I will exchange. So instead of silver stat, it will be a what? This nether belt. Instead of this nether belt, it will be a silver stat. That's it. Okay. Now here we got two new rows. AHA, nether belt, John D. Now if this row exists in the table, yes, you can see here exist. What about this one? AHA, Silverstedt, William M exist? Yes, you can see this exist. Right? So after swapping, we got two new rows, and if those rows exist in the table, it means what MVD also exists here. Okay.
We have to do this for all the four tuples.
So we have to do this for all unique value of alpha here. Once we check for AHA, that's it. We have to check for OSO then. Okay. You can take any two tuples. Let's say, for example, we'll take this one and this one here, right? Again, if I just exchange the beta value, I will get nether belt, I will get silver stat here. So AHA, nether belt, William M, yes, present. AHA, silver stat, John D, yes, already present here, right? You can also check for these two things, any two tuples, but same left hand side value and exchange the beta value. Okay. You can go with this one and this one as well. But here you can see it is Netherped, it is Silverstedt. So AHA, Netherped, Christian G, yes, already you can see this was row. Again, same row we got.
So what is R here?
Where R?
What is R? Like T3 of R minus beta is equal to T2 of
Yeah.
R minus beta. Then what is the R here?
R is all the attributes here, course, book, and lecture. Okay. And beta is basically
Like
this
we
attribute.
will take it as count.
No, R minus beta means what? Here beta is basically book. R is basically course, book, and lecture. So course, book, and lecture minus beta is basically book. In the output, I am going to get course and lecture here. Okay. So R is all the attributes of relation here. And I'm subtracting that attribute from that particular R here. Okay. So R is basically all the attribute, course, book, and lectures, right? And here beta is basically this book here. So if you look at this one, let me write it down. Here R is basically A, B, and C. Right? So R is basically A, B, C here. If I say R minus beta, and beta is basically, let's say for example, A multi determines C. So R minus C means what? A, B, C minus C. So I will get A, B in the output. Okay. We are doing a set operation here. That's it. So we are removing that particular attribute from the entire R here. And then we are checking whether that exists or not, satisfying or not. Okay. So let me prove this particular thing here, what we have discussed. So let's say, for example, we have A, B, C, we have three things. So let's go A1, A1, then we have this B1, then we have this B2, then we have this C1, then we have C2, right? Now, why A1, A1? Because by definition, we have said that in R such that T1 alpha equals T2 alpha. If there are two tuples, then only we can apply the concept of MVD. If only one tuple is there for that, no need to check for MVD. Okay. So here what I have said alpha A1, A1. Now just apply this thing. We have taken these two tuples. Beta is present here, that is B. I will swap the beta here. So here it will get B2, here it will get B1. So I got two new rows. What are the two rows? A1, B2, C1, A1, B1, C2.
C2.
This is what my entire table will look like in the case of MVD 8 multi-determine B here. So I got these two rows, and these two rows must be present inside my table. Now, if you look at all the relations, it is like that only. So T1 alpha, T2 alpha, then all four alpha must be same. You can see all alpha is basically a same. Then we have T3 beta equals to T1 beta here. Now T3 beta is equals to T1 beta. Now if you look at here, this is my T1, this is my T2, but if you look at, I can write this as this one and this one. So I can consider this as basically my T4, this is as my T3. Now you can see T1 beta is equals to my T3 beta, right? You can see here. Now, once I have fixed that tuple here, I have to satisfy for all the conditions. I cannot change the things. So T3 equals to T1 beta. This is fine, right? Now, what about this one? T3 R minus beta equals to T2 R minus beta. So T3 and T2, right? So R minus beta is basically what? AC here. R is A, B, C, beta is V. So we are subtracting that. We got AC. Now AC must be same for T2 and T3. Now we have A1, C2, A1, C2. You can see again satisfied. Check for this condition. T4 and T2 beta must be same. So T4, T2 beta. So B1 and B2 and B2 is same here. That is fine. So what got after swapping, right? Then next for T4 R minus beta, T1 R minus beta. So T4 is basically this one. T1 is this one. Again, AC is A1, C1, A1, C1. You can see all the conditions are getting satisfied here. So you can simply apply the trick. You can just follow this one. Take any two tuples such that we have same alpha value, swap beta value. You are going to get two new rows. If those rows are present inside the table, that's it. It is means every day exists here. Okay. Now, can we apply for these two rows, T1, T2? If I swap these two, am I getting a two new rows or same rows here? So basically, after swapping, also I'm
New
getting
rows.
the
So we will get new rows because Silbert set John D, Silbert set William M, and then we will
already
if we
present, na?
change- Yes.
So even if you exchange the same, because beta is same, even if you swap, you will get the same two rows here, right? It means it is already exist here like that. So it should satisfy for all the unique alpha value. If I just remove this one, then it's satisfying for AHA, but not for OSO because only one thing is present. It means what MVD does not exist here. Even if satisfying for AHA, but not for OSO, MVD does not exist. So MVD should exist for every unique alpha value. Okay. If I add here FPA, only one row here, satisfying for AHA, satisfying for OSO, but not for FPA, it means MVD does not exist. Okay. So the moment we add the rows here, MVD will get a change. Okay. So it's the concept of joint dependencies, all these things.
So OSO and silver are these are interchangeable, na? OSO and silver.
Yeah.
Both are these are there. Then why not exist, sir?
No, these are present. Even if I swap this, we are going to get same two things, right? So this is fine. MVD exists. But what I'm saying, if I remove this entire row from the table, only one OSO is present. So by definition, we don't have another tuple for that. So MVD will not exist for OSO.
Yes.
Okay, like that. Okay, so let's try to solve one question based on this MVD here. Again, you can see this question here from anyone solve this question, attempted this question in the mock test? No one. Okay. So again, like what I said, we have this A, B, C, D, right? We have this A determine B here, must determine B here. So here we have A, here we have B, C, D, E. We have two tuples already, 0, 1, 2, 3, 4, 0, 5, 6, 7, 8 here. Now, if I say MVD already holds on this relation R, which of the tuple must be in R? How to proceed this question? Yes, anyone? How to check?
T1 alpha equals to T2 alpha. We start by this.
Okay, so here we have A and B. This alpha, this is beta here. So we have T1, T2. So we can apply that condition. Keep the alpha values and exchange the beta value. If I exchange the beta value here, what I'm going to get here, it should be 5, it should be 1, right?
Yes.
So I'm going to get two new rows, 0, 5, 2, 3, 4, 0, 1, 6, 7, 8. So I'm going to get these two rows must be present inside the table, then only MVD can exist here. Now, is this in the option?
Yes, sir.
you can see this particular thing, right? So this thing we have done for A multi-determine B. But what about B determine D here? How to proceed now? I got the 4 rows based on the one MVD here.
Excuse me.
Yes.
After swapping the beta values, so we are going to add those new tuples into the table.
Yes, because then only MVD will exist.
Okay.
Okay. So we have just given 2 rows here, and we have mentioned that MVD exists on this particular relation R based on these 2 tuples. So we can apply that one. In order to check, we can check whether these 2 rows exist or not. But here we just have 2 rows. It means what? These 2 rows must be present inside the table such that this should be holding, right? MVD must hold on the relation R. So now we have got this one. Now what about the second MD? How to check for this?
Alpha should be taken from B, sir.
Yeah, so my left hand side basically is now alpha is basically B now. Now, which I have to take? But here we have 2 things now, 1 and 5. We have 2 beta value here, 2 alpha value here. We have 2 alpha value here. How to proceed now?
Maybe with any 1 or 5s.
So let's go with first, because by definition we have to consider left hand value must be same. So we'll take this 1 1 row first. So 0 0 1 1, and here we have 2 3 4, and here we have 6 7 8. Now can I apply this one again? B determine B multi-determine D. So keep the alpha value same, exchange the beta value. So if I exchange the beta value, what I'm going to get? Here it should be 7, here it should be 3, right? So 2 new rows will be what? 0 1 2 7 4, 0 1 6 3 8 here, right?
Yes.
Now is this row present?
Here we are changing the D value.
Yeah, because now we are dealing with B determine D here. Alpha is B, beta is D here. So keep the alpha value same, exchange the beta value. This is what we have done. Okay. So if in the option, if these rows are present, so that will be correct. But again, what we have to do? We have just checked for B equals to 1. But what about B equals to 5? Because this should be holding on every unique alpha value. This is what I have discussed. Now we have to check for B5 here. So let me write it down here. So here we have A, here we have B, C, D, E. Now let's check for 0, 0, 5, 5. Here 0, 5, 6, 7, 8. And here I have 0, 5, 2, 3, 4. Now again same thing, keep the beta value same, sorry, alpha value same, exchange the beta value. So what I'm going to get if I exchange this one, it should be a 3 here, it should be 7 here. I got 2 new rows, 0, 5, 6, 3, 8, 0, 5, 2, 7, 4, right? Now, is this present the option? 0, 5, 6, 3, 8 is present, right? That's it. So option B is also correct. It is also possible that these 2 will be in the option instead of this one, then it also be correct here, right? So this is how we can proceed in this particular question. Now, in order to exist these 2 MVDs, how many total tuples are required in the relation R? Tell me.
3 at least.
No.
Sorry, sorry, I said for columns.
Tuples, how many rows must be there such that both the MVD must satisfy? 8 here, right? 4 for this one and 4 for this one. There must be 8 rows in the table such that both should satisfy here. So this is what we got, 4 rows. Here we got 2 rows, and here we got new 2 rows. That is total 8 rows here. Okay. So you can expect this type of question also. If we have this MVD, this is the attribute, and how many rows, minimum number of rows are required. This is minimum number here.
Could you just take one example based on A multi-determines B, comma D, something like that?
Okay. So everything is same. We just change here A multi-determine B. Okay.
B, comma D, right? Like 2 attributes. Yeah.
Here, na? A,
Yeah.
B, D. Okay.
Yeah.
Now what is left hand side value here? BD, right? Alpha value is A and beta value is BD. Now again, keep the alpha value same, exchange the beta value. Now here we have B, here we have D, right? It means what? I need to exchange the beta value here. So it should be a what? 5
BD
and
should
7. It should be 1 and 3, right? So entire BD we need to swap. So 1, 3 swap with 5, 7 here like that. So I got two new rows, 0, 5, 2, 7, 4, 0, 1, 6, 3, 8. Okay, like that. So this will be a output row. So we need to swap both the BD combination here like that.
Okay.
Okay. So this is what we can say about MVD. And please do remember this, where it is. Okay. In the slide, this is basically summary slide. So in the original slide, you can see there are a few axioms applicable to MVD. So please refer to that as well. Here it is not mentioned, I guess. Okay.
Sir, if we have given a table and then asked for which functional dependency in the multi-value dependency will exist or not, how we see
Yeah.
check it?
So for FD is simple. Take any two alpha value, check it's satisfying the uniquely thing or not. If I say course determine books here. So AH determining books, AH determining data, is this satisfying here? No. So MVD, so FD will not satisfy here. Course determine book here. What
Sir,
if I say, huh?
for
Yes.
MVD I'm asking.
Yeah, for MVD, yes. So you can expect this table is given to you and check whether this course determined book or course determined lecture exists or not. So we have checked for course book. Let's check for course exist or not. So take any two tuples such that course value must be same. Okay. So let's take this one and this one. Then exchange the beta value here, lecture value here. So John D get replaced with Christian G, and here we have John D. Now we got two new rows. If those rows are present inside the table, in the original table itself, that's it. It means MVD exists for this particular thing. But we have to check for every unique left-hand side value. So if you see here, AH and another Christian G, where it is? Yeah, this is the row present. Another and John D is what? Another John D. Yeah, here you can see this row is already present. Okay. So you can see this rows are already present. It's satisfying for AHA, then check for OSO as well. So you have to check for every unique alpha value.
Okay, sir.
Okay. Okay. Great. So this is what we have discussed. So we have discussed about the week 5, week 6 in today's session. Anyone, any doubt from week 5, week 6? You can ask now. Any previous year question you are not able to solve, you can ask now.
Sir, where is this mock uploaded? Like, I'm not able to see in portal.
Portal is not visible. Let me check. Is a mock section, mock unit test, I guess, something like that. Just a second, let me check. Can anyone confirm it is visible or not, mock test?
No, it's not visible for me as well.
So you can see a mock test unit. In that we have, no, it's not visible. Okay, we'll release the mock quiz to you. You can just attempt that. Okay.
The next session will be on Saturday morning.
Yeah, next session will be in Saturday. So we'll discuss week 7, week 8. And then if you have any doubt from week 5 to 8, you can ask. Okay. So we'll, anyway, any doubt from week 5, week 6, any previous year question, you can ask now.
Sir, can I share my screen?
Yeah, okay. From week 5, week 6, right?
Yes, sir.
Okay.
Sir, for this functional dependency is not preserving data, no, but how it is lossy. each time I have solved it, I get lossless decomposition.
Can you zoom that or can you maximize that window? Just a second.
But if we do M1 union M2 union M3, then D is missing. That's why it is lossy.
So you want to ask for lossy or dependency preserving? Yes.
Sir, for lossy.
Okay, so you can see M1 union M2 union M3. So if we do that, we are going to get what? W, X, Y, Z, A, B, C. Where is D? D is not present anywhere inside the decompose relation, right? So our first condition itself is not satisfying. M1 union M2 union M3 must be equals to M. So D is not present, right? So that's why it's a lossy decomposition.
So I also have a doubt regarding
Okay.
MVDs.
Okay, any other question?
Yeah.
Yeah.
So I have doubt in this question.
Yeah, just a second.
So,
your screen is not okay. Yeah, now visible. Okay, so here we have the MVD relation for NF. Now we want to decompose this into 4NF. So will the MVD exist here?
Yes, sir.
Yeah, so it means it is not in 4NF, right?
Yeah.
Now when you decompose that table to in 4NF, now what we have discussed, there must be at least 3 attribute here, then only MVD can exist. So anyway, option 1 is not correct. Look at the option number 2, name and runs. And here we have name, team, and coach, right?
So here we don't have any MVD. We have to check for only the.
Only for table 3 here, right?
Yeah.
So here, if you observe name, team, coach. So if you observe in the original table, which MVD is name determine team, right?
Yes, sir.
So name determine team should not be present in any of the table having 3 attributes. So option 2 is not correct. Option
Sir, name determines team
okay.
is it MVD?
We have to check for that whether. So I can just swap the CSK with MI. So I will get Sharma CSK Mahila. Okay.
Yeah, we don't
Sharma,
have that, right? Sharma CSK Mahila is not there.
Not there. So team determine team multi-determine sorry, name multi-determine team is not a MVD here. Now check for name determine coach. Do we have that MVD? Name multi-determine coach. Sharma, then Steven Mahila. If we replace Steven Mahila, so we have Sharma CSK Mahila. Sharma CSK Mahila. Do we have that?
Sharma CSK. No, sir.
No, right? Okay. It means name coach will not exist. Check for name and runs.
Name runs is MVD, I guess.
Yeah.
So let's check. If I swap 50 and 90, so Sharma, CSK, Steven, 50. Yes, last row is there. Then we have Sharma, Yamai, Mahila, 99. Yes, third row is there. So it means name and run is a MVD here, right?
Yeah.
Yeah. So in that case, you can see name run is a MVD and that should not be present along with the third attribute. So name run, these 2 attributes are fine. But if I say name run with a team, name run with coach, that is not allowed here. So option B is correct here. I guess C and D is not correct because a team is present in the name run, right? B is correct? Yeah, okay.
Yes, sir. Thank you, sir.
Yeah, B is correct here. Yeah. So first we need to identify which MVD exists here. Okay, then only we can solve this question.
Sir, like I have one doubt in general. Say, for example, we are doing decomposition. We know that a table is in 3NF and it's not in BCNF, and we are doing some decomposition. Again, we have to start checking from 2NF, is it? Or we can assume that decomposed relation is also in 3NF, like that?
No. We have to start with again a 2NF thing also. We have to check. It is possible that when you decompose, it is not in 2NF.
Okay.
Yeah, so we have to check for that as well. Okay, can anyone refresh your portal and see whether mock 2 quiz is visible or not? Can anyone just confirm? Just check mock test unit and then mock quiz 2 is visible or not.
Yes, sir, it's visible.
Visible, right? Okay. You can try to solve those questions now. Yeah. Okay. A deadline, I guess. I will set. Okay, no worries. Okay, so that's it from my side. Try to solve the remaining question from mock test. In the Saturday session, we'll be discussing week 7, week 8. So only week 7, only important thing is Python and database connectivity, and rest is just the theory part. So even if you go through the slides, that is good enough for quiz 2. Okay. But in week 8, we have few important topics like BS3, and then we have LRU, MRU, those topics. Okay, so we'll be discussing those things. But in week 7, you can just simply go through slides. That is good enough for week 7. Okay. So that's it from my side. Thank you. All the best for quiz 2.
Thank you, sir.
Thank you, sir.
Chalo. Bye bye. Good night.
Thank you, sir.